This is the fourth lecture of quantitative big imaging. Today we are going to talk about segmentation and discrete structures. And this first part will be about image formation and following by thresholding. The lecture is recorded instead of a classroom lecture, which would take place on March 16. So this will be uploaded in advance and you can enjoy the lecture online. Today's lecture, we have a couple of topics, and actually this list includes probably 4 lecture recordings. So the first part will be about the image formation, followed by thresholding on also on different types of images. And then is the question how to select a good threshold. Some about implementation, followed by morphology, which is kind of our cleaning squad. And then we will look also into partial volume effects. To run this lecture, I again need a couple of modules. And I think by now you should know most of these. There's a little bit added here. Plotly is a plotting library, which we will use for 3D plotting. And also I'm using TIFF file. It's a library for loading and writing TIFF images in different formats. In particular, if you have floating point data in TIFF files, this library is the go-to. So now we look at some applications. We can have very simple materials where we have 2 phases. Could be bones, cells, some kind of material, added manufacturing, printing, etc. And those are quite easy to handle. But then we can also look into other material, that way we have more than a single channel of depth in the gray levels. We can have multiple phase materials. We could have filling holes in materials, segmenting fossils, and even try to segment the cortex in brain imaging, which is actually quite a challenging task. And you have actually one of those images here to the right. And the cortex is located in this region here. And as you can see, it has gray levels which are all over the image. So we need some really smart way to segment this, and it's not obvious. We will try doing some attempts in the next week lecture, but you will see how hard it is to actually do this segmentation. Then there is some useful literature. And again, John Ross comes at handy. And actually segmentation and the basic thresholding is something you can see in essentially every image processing book, but let's stay with John Ross. Then we will also look into ROC curves. That will be a little bit later in this lecture. So, first, a little bit about motivation. Why do we do imaging experiments at all? So, first idea could be that we want to explore some sample to visually and qualitatively examine samples and looking at difference between them. And when you explore, you don't always need so much prior knowledge or expectations, but you just browse around an image and see what things can I actually see here. Sometimes, of course, it helps to have more knowledge about the sample, because then you can more specifically pinpoint those things that are interesting. Another reason would be that we want to test a hypothesis, and for that we need a quantitative assessment, which is coupled to some kind of statistical analysis. So, for example, does the temperature affect bubble size in some foam? Or is this gene important for the cell shape? And maybe looking at some effects in the bones. Could also be that does higher canal volume make bones weaker? Or is the granule shape, does it affect the life expectancy of a battery? So many such questions could come up, but it can be hard to really put them down in words that can be programmed and analyzed in your analysis. So, for example, if we look at a cell, then we have different morphological features here. We have, for example, the nucleus, capsule, cell walls, plasma membranes, etc., etc. And all this are things that you may want to look into in a microscope image. And it's not always so easy to spot these things. Sometimes they're just blurry blobs. Sometimes, if you have a higher resolution image, you can more specifically see what they are. So, now we want to test a hypothesis and see how big the cells are in some tissue. And for that, in this case, we do a tomography experiment where we have a piece of bone, and from there we extract very many projections which are then reconstructed into tomographic slices. And there you can see now the structures in the image. You have the bone itself, you have some marrow, I think, and such an image results in maybe a good 2.5K cubed voxels, and maybe even in 32 bits because we want high precision to get good contrast. And that would give us 56 gigabytes of data per sample. Now, if you remember from the first lecture, we may have even up to 1,000 such samples because we want to look at different genetic features, different ages, different whatever. A lot of different variations in the data set. And once we have reconstructed this data, we want to do some filtering and pre-processing. And maybe 20 hours of computer time later, we still have 56 gigabytes of data, but less noisy. Or actually, to be really truthful, you would have 112 gigabytes of data because you don't directly throw away the raw reconstructions just because you filtered it. You may need it again. So it's way too much data, and we need to reduce this in order to be able to handle it. There are even few computers that can handle 56 gigabytes at once. And then, don't to mention that you may need to have this image maybe 3-4 times in the memory to be able to really analyze it. So it's really a huge amount of data that we are looking at. So what do we want in the first place? First, we want some single numbers describing the image, or maybe a collection of numbers. Could be the volume fraction of voids, for example. Could be cell count, or maybe a little bit more advanced, the average cell stretch. So if the cells are not perfectly round, how much are they stretched? We can also maybe want to look at the volume variability, and all these can actually be measured directly from the images. Now, why do we do segmentation? First, we want to identify relevant regions in the image. And there are quite many tasks available to solve this task, segmentation. And the question is, what is actually what you need? Sometimes you can use a simple threshold, as we will look at soon. Or else you may need a very heavy machine learning approach that finds the features that you want to look at. So here we have to choose wisely, and here it's quite important to think about Occam's razor, which is that the simple solution is usually the right one. But it's actually the simplest solution that gives the answer. So you may have to try different approaches, realize, okay, that one was maybe not the right one, and then you add on more and more advanced, sometimes with guidance of prior experience that, okay, you know, if it looks like this, then you may have to take something in that direction of a certain kind of segmentation. And this lecture today will not be so much about advanced segmentation techniques. That will come next week. But we will start looking into how to do the segmentation and also some evaluation of the results. And in particular, this can be also tricky if you have unknown data. So the less you know, the harder it is to do the segmentation. Just before we start looking at segmentation itself, I just want to review some about filtering and image enhancement. And as you may remember from the image enhancement lecture, we have some ideal case of what the image should look like. The sample is out there in the reality, it has some dimensions, but when it's irradiated or observed using some kind of radiation and captured by an imaging system, then you may add a lot of blur, noise, artifacts, etc. and then you have a quite messy image to analyze. And this is more or less the workflow where you have what you measure, so it's sample plus some noise and artifacts. And we are essentially only interested in a nice image where you see the features that you're after. And let's see what you can do. You have, for example, that hopefully your filter is enhancing maybe 90% of the real information and suppress the noise to be maybe 10% of it what it was from the beginning. If you have a bad filter, it would be the reverse. So you would really enhance the noise and everything you don't want. So that you have to watch out for, and you probably reject those pretty soon when you see it. And what we get from an image modality depends a little bit on how it's done. In this case, you see a radiograph of a rubber duck with some electronics in it. So this is the kind of rubber duck that flashes when you put it in water. So you can see that there are different features in it. And what we can describe when we look at this image is we can see, for example, the gray level distribution. Here you can see we have a large peak, which corresponds to the background. And then you have some very widely distributed number of gray levels throughout the image. And what we can see in this one, we can of course just take a look at it. It's maybe already a good thing. But we could also, by the eye, we could count. We could say that we have maybe 8 solder points on the PCB. Or we can also describe what we have in the image. So here we can say that the batteries are in the bottom. Those are the dark pieces down here. We can also say that we have some solder spots, that it's a hollow thing. So we have like a thin skin at the perimeter of this rubber duck. We could also look at some morphometrics like tracing the outline of the object or some substructures in it. So there is a lot of things we can do with this image already. Then how you approach the segmentation depends a little bit about your background, where you come from. So you have the experimentalist approach, then you know you want these and these features, and those you will try to enhance in best way. The computer vision approach, on the other hand, looks at filters and numbers and algorithms in order to extract information from this image. Then with the deep learning, then you actually require that you have some prior knowledge. So you need some kind of pre-labeling of the objects before you can actually do anything. So it's very result driven. So someone has to tell these algorithms that what they should do. This is what this table tells, that we have for the experimentalist, you have some problem-driven approach, and computer vision deep learning is more result-driven. When you look at the model of an imaging system, you in principle have some kind of excitation, could be light, could be X-rays, could be neutrons or something. This radiation goes through or reflects on the sample, and from that you get a response which is captured by the detector. So we have pretty many different imaging modalities, and in principle they have more or less the same underlying equation, where you have a function which is a system which takes the stimulus, the excitation, and some sample response to this kind of radiation. And if you look at direct imaging in a simple case, we have maybe a bit uneven illumination, and then we would look at, for example, the beam profile here. In this case, it's an X-ray image acquired by a flat panel detector, and this, for one thing, has a quite inhomogeneous response, and you can even see the stripes which correspond to the amplifiers on different segments of the detector. We also have some detector bias, so each detector pixel has some kind of bias built in. Sometimes it's just a flat noise background, which is at some level. In this case, the detector is really messy, so it gives you a quite rough background, and in order to get the real image you need to process the image and get the final information you want. And if we look at profile across the image, you can see here that we have the beam profile. Well, it's almost flat, so it's not too bad, but there is maybe an increase towards the middle. If you would look very closely and maybe also take out the bias, you would see that there are actually small steps here across this profile, but it's hard to see actually on this plot. Then you have the detector response, and you see that that would be the green line. And finally, we have the image as we would expect it. Actually, this is a normalized image, which I multiplied by 11,000 to bring it up to the level. Otherwise, it would be between 0 and 1. And this is actually, the orange one is the actual information that you want to look at. In absorption imaging, you are usually describing the system, or no, the interaction between the radiation and the sample by Beer-Lambert's law, which tells us that we have some kind of illumination, which we multiply by the exponential of minus some coefficient times the distance. And that is the response by the sample. And alpha is quite a complicated thing. It can be depending on the density. It can be depending on the density of the element that is in there, or the molecule that is in there, and also the microscopic cross-section, and so on. So it's a really complicated constant, this alpha. But it tells how much the beam is attenuated by this material. And to segment this, we can have either, sometimes there are just two distinct components, so you have material and air, but it could also be more complicated, that you have mixes of different elements on the way along the beam, and sometimes could also even be that you have vector value data. You could have color images, which have mostly in the computer RGB values. Could also be tensors, spectrum, etc. But then we come into more complicated segmentation models. So let's look at a numerical example where we have three materials with different alphas. We have alpha 1, 2, and 3. And they have average values of 1, 2, and 3 as well. But they have different standard deviations. And looking at this, you can see that material 1 mainly takes up this piece of the attenuation, material 2, this piece, and material 3, this piece. And when you measure it on the detector, this is what you see, that material 1 has a very wide spread. Then when you come to the heavier materials with higher attenuation coefficients, it gets more and more narrow. But as you remember, Beer-Lambert's law has an exponential, and in order to get the attenuation coefficient, we have to compute the natural logarithm and even change the sign. And then we can see that the distributions are now more like what we would expect, that we have something around 1, something around 2, and something around 3. And also the width, the first two here, they are more or less the same, and the last one is much wider. And that makes sense if you look back on these descriptions. And the thing is, when you measure your data, you not only have the illumination, but there may also be detector bias, which I described before with the flat panel detector. So normally, when you want to compute your transmission image, you compute the division of the measured image minus the bias image, and then you take the illumination minus the bias image as well, because this bias is included in every image. And the transmission image gives you this exponential of the integral through the material of different attenuation coefficients. Once you normalize it, then you have a very nice image. The values should ideally be between 0 and 1. And 0 means that there nothing between the source and detector, so we're just shooting through air. And then if you can have a value between 0 and 1, and that means the sample attenuates to some degree, but not fully. And if you have a 0 in the transmission image, it means that the sample is completely opaque to the radiation. So for example, if you have too thick layer of lead with X-rays, you will not see anything. I said that the transmission image is between 0 and 1 ideally. There are other factors that come in. For example, noise may spike above and spike below these values. And can also be that if you maybe have acquired one image at some source condition, and then the source changed temperature and maybe added or changed the intensity with that, then you would have fluctuations between the two, and then you have to actually correct the images for these fluctuations before you get a value between 0 and 1. And now let's take a little example using mammography. So now we're talking about, again, a radiograph. And the equations we have already worked with. So we have, again, Beer-Lambert's law. And now we actually look at an image. So we have different attenuation coefficients on X and Y positions. And on every position in the image, we also have different distances. And that gives us a nice line, or it can also be more generalized, doing it as a line integral instead of these distances. So it depends a little bit on what model you're using. And now when we want to interpret these radiographs, we have, as we said, attenuation coefficient, and we have thickness. And for example, we have that air has an X-ray attenuation of 0. There is nothing coming between. And breast tissue would have a 0.01, so it's not very much. And if you just have two different materials, then you can actually change the integral into a sum, so it's easier to calculate. Our breast phantom is, in this case, just a half ball, and that is what we visualize here. And this 3D plot is actually made using the Plotly library. And if you want to see how that works, you can actually look at the code, which I have hidden now in the lecture, but it's in the notebook. So now we want to set up the transmission image. We have that the alpha for breast is 0.01. And the pixel size is 0.1 centimeters. That is actually a thing, that the attenuation coefficient is traditionally given in per centimeter. So we have to scale it now to get a millimeter pixel size. The breast volume is multiplying the breast alpha times the breast mask. The mask was just zeros and 1, and now we have got locally attenuation coefficient. And what the detector sees is now the sum along the line of this half sphere, the breast. And then the sum is negated, and then we compute the exponential. And we multiply the whole thing by the pixel size. So now we have, with this equation, we have now the thickness, the optical thickness through the sample. And that would look something like this, where we have different transmission values. And you can also see here what the pixel count is. And low values, or relatively low values, you go here from 0.9 till 1. So it's not a very low value. And that shows now the distribution of the gray levels in this image. Now we want to compute the thickness of the breast from this model, and actually using the information from the detector. And what we do is we compute the negative logarithm of the detector information and divide it by breast alpha. And that gives us now the thickness. And now on the x-axis, we see that the breast thickness with 10 centimeters has this value. And then we have a lot of pixels which are just void. And so that's all the black outside here. And that would be the distribution we are looking at. So that can also be visualized, that we have the thickness is here, the thickest place, and out here we have the air. And as you can see now, if you remember, the model that we used actually had a half sphere, but this one is more like a quarter sphere. And that is because now we have summed all information, and we don't have any depth information along the ray. So what is alpha if alpha is not constant? Then we can maybe run into problems, or actually that is what we want to see, because if we have a dark lump in the breast, that could be interpreted as something that shouldn't be there. But now, as we have two components, when we compute the transmission image, that would be the thickness and the attenuation coefficient. It's not easy, it's not obvious if the change in the image is caused by something that is got thicker or if it's got a different density. And now we can look at how we change. Now we have added something in this area here, and we don't really know what is the cause of this. And actually the only way to really know it would be to make a tomography, but usually, given the fact that the breast should be more or less homogeneous, a dark thing would probably be something that is not healthy. And now we can compute again the detector image, where we see that there is this squared lump. And now we can do again the same thing that we did before, computing the negative logarithm and divide it by the attenuation coefficient that we would expect it to be. And then we see that we have different thicknesses, and all of a sudden we see that we have very many pixels with a different pixel size than we had before. So we have now a redistribution of the gray levels in the image. And that is then our indication that something is wrong. And if we look at the thickness profile with a lump, it doesn't really look like a breast anymore, but it has something that needs to be taken care of. So this brings me to the end of the image formation part. And mostly we can say that images from detectors can not directly be used in your analysis, but you have to normalize it in order to make it really useful. And also information in transmission images can be difficult to interpret because you have the ambiguity if it is caused by the thickness or by the attenuation coefficient. And this is the end of part 1. And stay tuned, and we will continue with the segmentation part, introduction to segmentation.